Today, we are going to be deriving Kepler's third law. Okay, let's get started. So what we have here is we have planet A and planet B going around the sun. So they're orbiting around the sun, and they're not necessarily circular orbits, okay? They can be elliptical. In fact, most planet orbits are elliptical, so we can just say that's the case. My goal is to find a relationship between the average distances between these planets and the sun, so their average distances, and the time it takes for each of these planets to go around the sun. Is there some sort of relationship we can draw from that? Now, we can derive a relationship like that using Newton's law of gravity. So let's just start off with that. So Newton's law of gravity is the force of gravity between these planets and the sun. So we can just say, we're going to just focus on one planet for now. One planet, and see if we can do anything from there. So let's just say we have planet A. The force of gravity between planet A and the sun is just going to be using Newton's law of gravity. So I'm going to say G, and I'm going to say mass of the sun times the mass of the planet A, right? So G, m1, m2 over r squared. You probably know that. Divided by r squared, which is the distances between the centers of those two planets. So that is Newton's law of gravity. Now, how can we continue on from here? Well, there's this other relationship that we can derive from the Newton's law of gravity, and that is the acceleration due to gravity, or the gravitational field strength. We're going to think of it as the acceleration due to gravity, because this can help. Most people understand it as best that way. Now, if I want to do that, I have to know another thing to write Fg as. Well, isn't this kind of the force of gravity on something? It's like the weight of an object. For example, I have a weight. I have a certain weight on Earth. And so you could think of the acceleration due to gravity as the centripetal acceleration of planet A. Now, granted, planet A, the acceleration due to gravity of planet A around the sun is always changing, right? And the reason why is because it's an elliptical orbit, right? We'll get further into that. But isn't the force of gravity on planet A to the sun just mag? So it's the acceleration, it's the force of gravity acting on planet A to the sun, right? It's kind of like just the weight of an object on Earth. It's just applying at a large scale, right? And so that is going to be that. And we have G ms ma over r squared. Okay, now, what can we do? Well, we could cancel out the mass of planet A. And we're left with G equals capital G ms over r squared. And some of you are familiar with that. So we can just continue on from here. What can we do once we have this? Well, isn't there something we can rewrite G as? You're probably thinking, oh, well, this is the centripetal acceleration of this planet, right? And we could say, oh, well, isn't that just v squared over r? Sure. And so we do that. We could say G is just v squared over r. Remember, this is the speed, or the circular speed, of planet A. So I'm going to say planet A. All right. I could say centripetal acceleration. I'm just going to say v for now, actually. I'm not really concerned about whether it's A or B. It could be any of those planets. This is just going to help us understand that, right? And so mass of the sun over r squared. Now, we can solve for v as well. Why don't we just solve for v, right? So here's the thing. How do we do that? Well, we can multiply r on both sides to get rid of the r on this side. See that? So I'm multiplying by r on both sides of the equation. And I get v squared is equal to gms over r. And then we solve for v by taking the square root of both sides. And since circular speed is always positive, it's just the positive square root of that. All right, so this is just the circular speed of any planet. Now, here's the thing you're probably confused about. Isn't the circular speed changing if it's an elliptical orbit? There's this little thing that we haven't discussed. How does this work for an elliptical orbit. And I'm not going to go into the full details. I'm just making this as simple as possible. You can think of this as the average speed and the average centripetal acceleration. If it's the average centripetal acceleration, then we're keeping that centripetal acceleration constant, technically, because it's an average. And so we can assume it's a circular orbit if we think of this as the average distance between the planet and the sun. And remember, our goal is to find a relationship between the average distance between the planet and the sun, right? And the time periods it takes to go around that in the sun. All right, now that we have that understood, what can we do now? Because we still haven't found any sort of relationship. Well, remember, maybe we don't know exactly where we're heading, but we know that we can rewrite v in some other way as well. So we rewrote FG, G, now we're about to rewrite v in some other way. So let's just do it. Let's just see what we can do with this thing. How far can we go until we hit a brick wall, or will we actually find what we're looking for, right? Isn't the average speed of an orbit, let's just assume it's circular now because we understand that. Isn't it just the circumference of the circle divided by the time period it takes to go around that circle? So you're probably familiar with 2 pi r over t, which is the circumference of a circle, or the distance the planet travels along a circle divided by the period, or the time period it takes to make one circumference, right? That would be the circular speed. And that makes sense. Is equal to the square root of gms, gms, I'm going to just say gms over r, right? What do we do now? Well, here's what we can do. Notice how we can put together, remember, this is an average distance now. This is average distance. We can actually group together average distance and the time period, or this is the period, right? So the period to make one revolution around the sun, right? That doesn't change if we're just doing an average distance, right? The period is still the same, whether it's elliptical or just the average distance, right? It doesn't matter if we think of this as a circular orbit, it's still going to be the same. So, if I square both sides, I can group r and t together. So I'm going to square both sides. And so this is where things start to get a little weird for some reason. For some people, it's fine. I'll do my best to explain this. So if I square both sides, we know the square root goes away. So we're left with gms over r, right? Now, what do we get on the other side? That's what we got to start to focus on. Well, we know that if we're squaring something with multiplication and division, it's 2 squared times pi squared r squared. So it's going to be 4 pi squared r squared all over t squared, right? Now, another thing that we can do is we can group together r. Can we just multiply r on both sides of the equation to do that? Because if we do that, we get rid of the r over here, and since we're doing r times r squared, we get r cubed. And so this goes away. We're left with 4 pi squared r cubed all over t squared. So this is cubed equals gms. Now another thing. We divide by 4 pi squared on both sides. So let's just do that. So we're dividing by 4 pi squared on both sides. So hopefully you saw what I wrote before, because that's basically what I'm doing. So it's gms all over 4 pi squared. This is what I get. Now here's the thing. Isn't this a constant value? It won't change. The mass of the sun won't change, reasonably speaking. G is a constant, and this is constant. So this is equal to a constant. So we can say this is true for one planet. And we could say, oh, well, if we do it for planet, let's just say this is planet A, the average distance between the sun and planet A, the period it takes A to go around the sun, equals the same that for planet B, right? Because if we were to do it, we'd get that same constant, right? Because this works for any planet going around the sun. And so that means since we're equal to a constant, we can say that these things are equal to each other. So those things are equal to each other. Right? Remember, average distance, right? Because we did that, now we're using average distance. Now, we can algebraically manipulate this to say You could just algebraically manipulate and you would eventually get this. RA over RB cubed equals, I would pretty much, this goes here, this goes here. So it's going to be, this would be B. TA over TB. This is just algebraic manipulation. I'm not going to show all that work. I'm pretty sure you can algebraically manipulate things. And so this is what we get. Kepler's third law. I can't even say it in words. The average distance between a planet and the sun is directly proportional. I said it wrong. The cube of the average distance between a planet and the sun is directly proportional to the period of that planet squared. Okay, yeah. This is Kepler's third law, derived from Newton's law of gravity.